All right, so this video we're going to go over testing for a unit root. So we're going to test for a unit root. Testing for unit root. I'm sorry, I keep coughing. I feel like I've been coughing through all these videos. So testing for unit roots. So let's do a simple AR first order process. So we'll let's let yt be equal to, let's do alpha plus beta yt minus 1 plus our error term. And epsilon is still going to be IID with a mean of 0. And let's say that the expected value of yt, I'm sorry, not y, the expected value of our error term given previous values of y is 0. So the expected value of our error term given previous values of y is 0. So it's just a AR, just an autoregressive first order process. So we want to know, is there a unit root? Is it a stable process? So in order to test for this, we're going to do an hypothesis test. So let's set it up as a null hypothesis, being that there is a unit root. So you put the burden of evidence on it being so you have to prove that it's not a unit root. So we're assuming that it is, and we have to prove that it's not. So the alternative hypothesis would be that it's not does not have a unit root. So this means that it's our beta is going to be less than 1. So remember, for this, we're kind of assuming that it's positive numbers, because if it was greater than 1, then it's not stable. If it's equal to 1, then it's not stable. And this is absolute value of 1. So it could be 0.5, it could be negative 0.5. So in order to be a stable process, to be a stable process, in order to be a stable process, the absolute value of beta has to be less than 1. So it could be 0.99, it could be negative 0.99, which, I mean, that's pretty close to 1, so that could be a problem. But it has to be, the absolute value has to be less than 1. So to test this, we cannot use a t-test to test to do a test for this. We cannot use the t-distribution. So this is tough to do. This would be tough to do if you were not using a t-test. But there's a way to simplify it. There's a way to simplify it. And to simplify it, we can subtract the y of the previous value of both sides. So we can say y of t minus the y of t minus 1, so the previous value, is equal to alpha plus beta of the previous value minus the previous value plus our error term. So this would give us the following. Let's say it would give us the change in y is equal to alpha plus, and let's use theta. So plus theta multiplied by the previous value in our error term, where theta is going to be equal to 1 minus, I'm sorry, not 1 minus, it's going to be equal to beta minus 1. So this is useful because with theta, we can now use a t-test. Before, this is, we're kind of stuck at it 0 or greater. But with now with this, we can be, this can test for this, whether the absolute value is less than 1. So now we can test, is there a unit root? And this is known as a Dickey-Fuller test. So this is a to test whether or not this, our beta, absolute beta, is less than 1. To test for this, now we can use a t-test. We can now use a t-test on theta. Let me use t-test for theta. And this is known as a Dickey-Fuller test. So now we're going to apply it. We're going to apply it to, we're going to do an example. So I'm going to clear all this. So in our example, this comes from Woodridge in his introductory econometrics textbook, but it's a good example. So we're going to do a unit root test for 3 month treasury bills, and it's quarterly data. So for this, we get the following model. So you run a model, you estimate the parameters, and we get, let's use RT for the 3 month rate. We get the change in RT is equal to 0.625. So this is alpha with a standard error of 0.261. So this is standard error minus 0.091. This is our beta. And the standard error is 0.037 multiplied by our previous value. So with this, we can now do, so real quick, these are standard errors. So this would be the standard error of that respective coefficient. So now we can do a t-test. We can do a t-test to test whether or not there is a unit root. So let's before we do the t-test, let's review what this is going to be. The null hypothesis for this is that there is a unit root, and we have to prove that there isn't. So the burden of proof is on this side. We have to prove that there is no unit root. So now let's do a t-test. So remember, for the t-test, it's going to be your estimate for your coefficient, which is negative 0.091, divided by the standard error, which is 0.0379 or 37. So this would mean our t-test, or our t-statistic, is equal to negative 2.46. And this, if you compare this to a t-table, we fell to reject the null hypothesis. We failed to reject the null hypothesis. Let's say H0 for the null hypothesis. So this would mean that that we can reasonably believe that quarterly data of 3 month T-bills is a random walk. It has a unit root. So you cannot really predict that. So for this version of the Dickey-Fuller test, we can only do one lag. There's another extended version. There's an extended version of the Dickey-Fuller test, which we're going to do in Python, where it can do a number of k-lags. So the steps for this by hand is a little bit more complicated, and to going over all of that is a little bit beyond the scope. But the augmented Dickey-Fuller test is where you can do more than one lag, and with that, we'll do it with some other stuff. So this was the Dickey-Fuller test, and this is how you determine, or how you can construct a hypothesis test of whether or not there is a unit root. And remember, in order for you to be able to build a, if you're going to do a time series model, if you're going to do maybe an AR model with some order of P, it has to be stationary. And in order to be stationary, it has to have a constant mean, and it has to have constant variance. And with this, there is no, you failed to reject the null hypothesis, so you can't build an autoregressive model on this, or an ARMA or moving average or any of that. So this is it for this video. In the next video, we will do it again, but this time we will do it in Python.